Dear students, in this video we are going to study about Ampere's circuital law, magnetic field due to a current carrying wire of infinite length using Ampere's law. Next, magnetic field due to a long current carrying solenoid, and also about toroid. Now let us study about Ampere's circuital law. Ampere's circuital law, this is used to calculate magnetic field at a point whenever there is a symmetry in the problem. So this is similar to Gauss law in electrostatics. Now let us see what is Ampere's circuital law. This law states that the line integral of magnetic field over a closed loop is mu naught times net current enclosed by the loop. Therefore, the equation can be written as closed integral of B dot dl equal to mu naught I enclosed. So this I enclosed is the net current linked by the closed loop C. Note that the line integral does not depend on the shape of the path or the position of the conductor with the magnetic field. This line integral, it is denoted by a letter this, like this. The integral over a line or curve, the symbol used is like this. Whereas the closed line integral means integral over a closed curve or line, symbol is like this, closed integral. Next, the magnetic field due to the current carrying wire of infinite length using Ampere's law can be calculated like this. So here is the current carrying state conductor and the Amperian loop for this current carrying state wire. Let us consider a state conductor of infinite length carrying current I, and the direction of magnetic field lines is as shown. Since the wire is geometrically cylindrical in shape and symmetrical about its axis, we construct an Amperian loop in the form of a circular shape at a distance r from the center of the conductor as shown. From the Ampere's law, we get this expression closed integral B dot dl equal to mu naught I. dl is the line element along the Amperian loop, which is tangent to the circular loop. Hence, the angle between the magnetic field vector and line element is 0. Therefore, closed integral B dot dl equal to mu naught I, where I is the current enclosed by the Amperian loop. Due to the symmetry, the magnitude of magnetic field is uniform over the Amperian loop. Hence, B closed integral of dl is equal to mu naught I. So for a circular loop, the circumference is 2 pi r, which implies that B integral dl limits 0 to 2 pi r equal to mu naught I. So B into 2 pi r equal to mu naught I. B equal to mu naught I by 2 pi r. In active form, the magnetic field is given by B equal to mu naught I by 2 pi r into n unit vector, that is n unit vector is the vector along the tangent to the Amperian loop, so unit vector. Then we study about the solenoid. What is a solenoid? It is a long coil of wire which is closely wound in the form of helix as shown. When the electric current is passed through the solenoid, the magnetic field is produced. The magnetic field of the solenoid is due to the superposition of magnetic fields of each turn of the solenoid. The direction of magnetic field due to solenoid is given by right-hand palm rule. Inside the solenoid, the magnetic field is nearly uniform and parallel to the axis, whereas outside the solenoid, the field is negligibly small. Based on the direction of the current, one end of the solenoid behaves like the north pole and the other end behaves like the south pole. The current carrying solenoid is held in right hand. If the fingers curl in the direction of current, then the extended thumb gives the direction of magnetic field of current carrying solenoid. This is shown here in 3.39 like this. Hence, the magnetic field of a solenoid looks like the magnetic field of a bar magnet, having two poles, north and south pole. The solenoid is assumed to be long, which means that the length of the solenoid is large when compared to its diameter. The winding knot to be always circular, can also be in other shapes. We consider here only the circularly wound solenoid as shown in 3.40 here. So these are the different types of solenoids. Now let us study what is the magnetic field due to a long current carrying solenoid. Consider a solenoid of length L having n number of turns like this. The diameter of the solenoid is assumed to be much smaller when compared to its length, and the coil is wound very closely. In order to calculate the magnetic field at any point inside the solenoid, we use Ampere's circuital law. Let us consider a rectangular loop ABCD as shown here in this diagram. Then from Ampere's circuital law, we have closed integral of B dot dl equal to mu naught I enclosed. That is given by mu naught into total current enclosed by the Amperian loop. The left hand side of the equation is given by cos integral of beta dl, that's equal to a to b integral beta dl plus b to c beta dl plus integral c to d beta dl plus integral v to a again beta dl. Since the elemental lines along BC and DA are perpendicular to the magnetic field, which is along the axis of the solenoid, the integral b to c beta dl is equal to integral b to c b dl cos 90 degrees, that's equal to 0. Similarly, integral d to a beta dl equal to 0. Since the magnetic field outside the solenoid is 0, the integral c to d beta dl is equal to 0. For the path along AB, the integral is given by integral AB a to b beta dl equal to b into integral a to b dl cos 0, that's b equal to integral a to b dl as cos 0 equal to 1. The length of the loop AB is as shown in this figure, that is given by h. But the choice of the length of the loop AB is arbitrary. We can take very large loop such that it is equal to the length of the solenoid L. Therefore, the integral is given by integral a to b beta dl equal to b times L, where L is the total length, and IB the current passing through the solenoid of the n turns. Then integral a to b beta dl equal to BL, that's given by mu naught Ni. So mu naught into Ni by L. The number of turns per unit length is given by N by L. Where N by L that is equal to total number of turns N. Then B equal to mu naught N Li by L, so that is equal to mu naught Ni. So this is the magnetic field. Since N is constant for a given solenoid and mu naught is also a constant. For a fixed current I, the magnetic field inside the solenoid is also a constant. Then here this solenoid can be used as an electromagnet also, which produces strong magnetic field. It can be turned on or off. Then this magnetic resonance imaging techniques, that is actually helping the physicians to diagnose or monitor treatment for a variety of abnormal conditions within the head, face, abdomen, and pelvis. So by using this medical test, it is possible to detect any problems in our human body. And actually this is made up of a superconducting wire, a solenoid which is made up of a superconducting wire which carries a large current to produce a strong magnetic field. And using that magnetic field, it is possible to examine various parts of the body, which is called MRI, which is magnetic resonance imaging. So here V into 2L and equal to mu naught Ni by 2L, that's equal to half BLN. Where the length of the solenoid and number of turns are doubled, you will have this equation BL V 2L, so N equal to mu naught 2Ni by 2L BLN. Then the number of turns becomes twice, but the length of the solenoid remains the same in this case. So here we have these conditions. First condition A, for this in this example, it is given. All the three conditions are discussed to calculate the magnetic field inside the solenoid. Next, we are going to study about the toroid. A solenoid which is bent in such a way that its ends are joined together to form a closed ring shape. It is called as a toroid, which is shown in this diagram. The magnetic field has a constant magnitude inside the toroid, whereas in the interior region, the point P, and exterior region, point Q, the magnetic field is 0. Let us consider the case if the open space interior to the toroid. Let us calculate the magnetic field Vp at the point P. We construct an Amperian loop 1 of radius R1 around the point P as shown here. For simplicity, we take the circular loop so that the length of the loop is its circumference. So L1 equal to 2 pi R1. And Ampere's circuital law for the first loop is given by closed integral is loop 1 Vp dl, that's for mu naught I enclosed. And the loop 1 encloses no current, I enclosed is equal to 0. So closed integral Vp dot dl equal to 0. This is possible only if the magnetic field at point P vanishes, that is Bp equal to 0. Next case, open space exterior to the toroid. Let us calculate the magnetic field BQ at point Q. We construct an Amperian loop 3 of radius R3 around the point Q as shown. The length of the loop is given by L3 equal to 2 pi R3. And by Ampere's circuital law, we have this equation, cross integral BQ dl equal to mu naught I enclosed. Since in each turn of the toroidal loop, current coming out of the plane of the paper is cancelled by the current going into the plane of the paper, so I enclosed is equal to 0. So cross integral BQ dl equal to 0. This is possible only if the magnetic field at point Q vanishes, that is BQ equal to 0. Now inside the toroid, let us calculate the magnetic field Bs at the point S by constructing an Amperian loop 2 of radius R2 around the point S as shown. The length of the loop is given by L2 equal to 2 pi R2. Ampere's circuital law for this loop is given by closed integral, that is loop for loop 2 Bs dl equal to mu naught I enclosed. If I is the current passing through the toroid and n be the number of turns of the toroid, then we have I enclosed equal to Ni. So S is given by mu naught Ni by 2 pi R2. If the number of turns per unit length is given by n equal to n by 2 pi R2, then the magnetic field at the point S is given by Bs equal to mu naught Ni.